Hello my friends, and welcome back to Sky Creative Channel. I'm your host, and today we're taking you on an amazing journey, from the rugged mountains of Algeria to the high-speed railways of China and the innovative bridge construction in Indonesia. Let's get started. Our first stop takes us to the breathtaking yet challenging terrain of Algeria, where Turkish construction giant Özgen Inşaat has undertaken one of the most ambitious highway projects in North Africa. The Karata RN09 road project isn't just about building a highway, it's about conquering nature itself, carving a modern transportation corridor through some of the most unforgiving landscape you can imagine. Picture this: steep mountain slopes, rocky outcrops that have stood for millennia, and weather conditions that would make even the most seasoned engineers pause. Yet here we are, witnessing the transformation of this rugged terrain into a vital transportation artery that will connect communities and boost economic development for generations to come. The Karata RN09 road project spans approximately 45 kilometers through the mountainous region of Karata, connecting the coastal areas with the inland territories. What makes this project truly remarkable isn't just its length, but the engineering challenges it presents. We're talking about elevation changes of over 800 meters, rock formations that require specialized blasting techniques, and terrain so steep that traditional construction methods simply won't work. Özgen Inşaat, with over 4 decades of international construction experience, brought their A-game to this project. They've worked in over 30 countries, but even for them, this project presented unique challenges. The company had to develop innovative solutions for everything from material transport to worker safety in this demanding environment. The project includes not just the main highway, but also numerous retaining walls, drainage systems, and safety barriers designed to withstand the harsh mountain weather. Every meter of this road required careful planning and precise execution. Now, let's talk about the fascinating technology that makes this project possible. First up is the controlled blasting technique. Unlike the old days of blast and hope for the best, modern road construction uses precision explosives that can fracture rock in predetermined patterns. Özgen Inşaat employs Swedish-made Atlas Copco drilling equipment that can create blast holes with millimeter precision. The drilling process uses computer-controlled hydraulic drills that can penetrate the hardest granite formations. These machines, weighing over 20 tons each, use tungsten carbide bits that rotate at speeds up to 300 RPM while simultaneously hammering the rock face. The result? Perfect holes that ensure the explosive charges create the exact fracture patterns needed for efficient rock removal. But here's where it gets really interesting. The company uses electronic detonators that can be programmed to fire in sequences measured in milliseconds. This technology allows them to control not just when the explosives fire, but in what order, creating a cascading effect that breaks the rock into manageable pieces while minimizing vibrations that could affect nearby structures. For earth-moving, they're using Caterpillar D9T bulldozers, absolute beasts that weigh 49 tons and can move 7.4 cubic meters of material in a single pass. These machines are equipped with GPS-guided grading systems that ensure the roadbed is built to exact specifications, with tolerances measured in centimeters rather than meters. The machinery lineup for this project reads like a who's who of heavy equipment manufacturers. We've got Volvo A45G articulated dump trucks that can carry 43 tons of material while navigating grades up to 35 degrees. These trucks use advanced traction control systems that automatically adjust power distribution to prevent wheel spin on loose surfaces. For precision grading, the team uses Caterpillar 24M motor grader equipped with 3D GPS systems. These machines can automatically adjust their blade position based on digital terrain models, ensuring that every section of roadway meets exact specifications. The operator doesn't have to guess. The machine knows exactly where it should be, placing material. The concrete work utilizes mobile batch plants that can be moved as the project progresses. These plants can produce up to 120 cubic meters of concrete per hour, with automated quality control systems that monitor everything from aggregate gradation to cement content. One of the most impressive pieces of equipment is the tunnel boring machine used for the project's 3 tunnel sections. This 12-meter diameter beast can excavate 20 meters of tunnel per day while simultaneously installing concrete lining segments. It's like watching a mechanical earthworm create perfectly round tunnels through solid rock. The construction process follows a carefully orchestrated sequence that would make a symphony conductor proud. It all starts with detailed geological surveys using ground-penetrating radar and core sampling to understand exactly what lies beneath the surface. Next comes the access road construction. You can't build a highway without first creating ways to get equipment and materials to the work sites. These temporary roads often require their own engineering solutions, including temporary bridges and switchback designs that allow heavy equipment to navigate steep slopes. The actual roadway construction follows a systematic approach: blast, excavate, grade, compact, and surface. But each step involves sophisticated quality control measures. Compaction is monitored using intelligent compaction systems that provide real-time feedback on soil density. The GPS-equipped rollers create digital maps showing exactly where proper compaction has been achieved. For the retaining walls, the team uses a technique called soil nailing, where steel reinforcement bars are driven into the slope face and then covered with shotcrete. This creates a flexible retaining system that can accommodate ground movement without failing. The final paving operation uses state-of-the-art asphalt pavers that can lay material in widths up to 16 meters. These machines are equipped with automatic grade and slope controls that ensure a perfectly smooth surface that will provide decades of service life. Hold on to your hats, folks, because we're about to witness one of the most spectacular displays of engineering prowess on the planet. We're heading to China, where the construction of high-speed railways has reached a level of sophistication that would have seemed like science fiction just a few decades ago. The project we're exploring today is part of China's ambitious high-speed rail network, designed for operational speeds of 350 kilometers per hour. That's about 217 miles per hour for us Americans. To put that in perspective, that's fast enough to travel from New York to Philadelphia in just 45 minutes. But building infrastructure that can safely handle those speeds requires engineering precision that's simply mind-boggling. What makes this project particularly fascinating is the extensive use of elevated track sections. Unlike traditional railways that follow the contours of the land, these high-speed lines take a more direct approach, soaring over valleys, rivers, and urban areas on massive concrete viaducts. We're talking about hundreds of miles of elevated track, supported by thousands of precisely engineered concrete spans. The scale of this undertaking is almost impossible to comprehend. The project involves constructing over 200 kilometers of elevated track, requiring more than 1,800 individual bridge spans, each weighing between 500 and 900 tons. And here's the kicker. They're installing these massive concrete beams at a rate of 3 to 4 spans per day using the most advanced bridge construction equipment ever developed. Now, let me introduce you to the star of our show, the SL 930 Bridge Girder Erection Machine, affectionately known as the Iron Monster by the construction crews. This magnificent piece of engineering is essentially a mobile bridge building factory that can pick up, transport, and precisely position massive concrete girders with the delicacy of a watchmaker. The numbers alone are staggering. This machine is 91.8 meters long. That's longer than a football field and weighs an incredible 580 tons when fully loaded. It rides on the railway tracks themselves, using specialized bogies that distribute its enormous weight across multiple axles. The machine can lift girders weighing up to 900 tons, which is equivalent to lifting about 450 automobiles simultaneously. But here's where it gets really fascinating from an engineering perspective. The SL 930 doesn't just lift these girders, it can position them with millimeter precision. The machine uses a combination of hydraulic systems, GPS guidance, and laser positioning to ensure that each girder is placed exactly where it needs to be. The positioning accuracy is so precise that the tolerance is less than 5 millimeters over a 32-meter span. The lifting mechanism uses a sophisticated system of hydraulic cylinders and steel cables. The main lifting frame can extend up to 40 meters in height, allowing the machine to work over existing structures or obstacles. The entire lifting operation is controlled by computer systems that monitor load distribution, wind conditions, and precise positioning throughout the entire process. What's particularly impressive is the machine's ability to work in a continuous production line method. While one girder is being positioned, the next girder is already being prepared for lifting. This assembly line approach allows for the incredible installation rate of 3 to 4 girders per day, each weighing as much as a fully loaded Boeing 747. The technology integrated into this construction process represents the cutting edge of civil engineering. Each concrete girder is manufactured to tolerances that would make aerospace engineers proud. We're talking about 32-meter-long concrete beams that are accurate to within 2 millimeters of their specified dimensions. The girders themselves are marvels of engineering. They're made from high-strength concrete with compressive strengths exceeding 50 megapascals. That's roughly 3 times stronger than typical building concrete. The concrete is reinforced with high-tensile steel cables that are post-tensioned to create a structural element that's incredibly strong, yet relatively lightweight. The manufacturing process uses automated concrete mixing systems that precisely control the water-to-cement ratio, aggregate gradation, and admixture content. Each batch of concrete is tested using real-time analysis systems that can detect any variations in quality before the concrete is poured. But perhaps the most impressive aspect is the quality control system. Every girder is subjected to load testing that simulates the stresses it will experience in service. Using hydraulic jacks, engineers apply loads that exceed the design requirements by 25%, while monitoring deflection and strain at multiple points along the span. The positioning process uses multiple redundant measurement systems. GPS provides overall positioning accuracy, while laser measuring systems provide fine-tuned positioning data. Accelerometers monitor any movement during the lifting process, and wind sensors ensure that lifting operations are suspended if weather conditions become unsafe. The logistics of this operation are every bit as impressive as the technology. Imagine coordinating the delivery of 900-ton concrete girders to a construction site that's constantly moving. It's like trying to deliver packages to a train that never stops. The girders are manufactured at specialized precast facilities located strategically along the rail line. These facilities operate 24/7, producing girders in a continuous production cycle. Each girder is manufactured to exact specifications for its specific location in the project, complete with pre-installed bearing assemblies and connection hardware. Transportation of these massive girders requires specially designed rail cars that can handle the enormous loads. These cars use multi-axle bogies that distribute the weight across longer spans of track. The entire transportation system is computer-controlled, with a GPS tracking that monitors the location and condition of every girder throughout the supply chain. The erection process follows a carefully choreographed sequence. The SL 930 machine moves along the completed section of track, positioning itself at the next installation point. The machine's support legs are deployed and leveled, creating a stable platform for the lifting operation. Meanwhile, the delivery train arrives with the next girder, which is transferred to the erection machine's lifting frame. What's remarkable is how this process continues regardless of what's happening below. The machine can work over active roadways, rivers, or even existing railway lines without disrupting normal operations. The entire operation is conducted from an elevated position, with the construction crews working safely above any ground-level hazards. Safety in this operation isn't just important, It's absolutely critical. We're talking about moving 900-ton concrete beams through the air at heights of up to 40 meters, often over busy roads and populated areas. The margin for error is essentially zero. The safety systems are as impressive as the construction equipment itself. The SL 930 is equipped with multiple redundant safety systems, including backup hydraulic systems, emergency stop capabilities, and real-time monitoring of all critical functions. If any system detects an abnormality, the entire operation can be safely stopped and the load secured. Weather monitoring is continuous, with automated systems that track wind speed, temperature, and precipitation. Lifting operations are automatically suspended if wind speeds exceed 20 kilometers per hour, or if precipitation might affect visibility or equipment operation. Each girder installation is monitored by teams of engineers using laser measurement systems and strain gauges. The positioning accuracy is verified multiple times throughout the installation process, ensuring that each girder is placed exactly where it needs to be for the track alignment to meet the stringent requirements for 350 kilometers per hour operation. Quality assurance extends beyond just the installation process. Once installed, each girder is subjected to additional testing using dynamic load testing equipment. This involves rolling heavily loaded test cars across the new spans while monitoring deflection and vibration characteristics. The innovations developed for this project are already being applied to high-speed rail projects around the world. The SL 930 technology represents a quantum leap in bridge construction efficiency, reducing construction time by up to 70% compared to traditional methods. This technology is helping to make high-speed rail construction more economically viable, which could revolutionize transportation systems globally. The precision and efficiency demonstrated here show us what's possible when engineering innovation meets ambitious infrastructure goals. Our final stop takes us to the beautiful archipelago of Indonesia, where we'll witness an elegant solution to a complex engineering challenge. The Timef Nindya Karya Dam project showcases how modern pre-stressed concrete technology can create bridges that are both structurally efficient and aesthetically pleasing. This project is particularly significant because it demonstrates how pre-stressed concrete bridges can be constructed in challenging environments where traditional construction methods would be impractical or prohibitively expensive. The Timef Dam project required a bridge that could span significant distances while minimizing environmental impact on the surrounding ecosystem. Let's dive into the fascinating world of pre-stressed concrete, a technology that revolutionized bridge construction in the 20th century and continues to evolve today. The basic principle is ingenious in its simplicity. Instead of waiting for loads to create tension in the concrete, we pre-stress the concrete by applying tension to steel cables before the concrete experiences any surface loads. The girders for this project use post-tensioning technology, where high-strength steel cables are threaded through ducts cast into the concrete. Once the concrete has reached sufficient strength, these cables are tensioned using hydraulic jacks that can apply forces of up to 300 tons per cable. This creates a compression force in the concrete that counteracts the tension forces that will be created by traffic loads. The beauty of this system is that it allows concrete, which is naturally weak in tension, to be used efficiently in structures that experience significant bending moments. By pre-compressing the concrete, we can create beams that are both lighter and stronger than conventional reinforced concrete beams. The steel cables themselves are marvels of materials engineering. Made from high-carbon steel with tensile strengths exceeding 1,800 megapascals, these cables can withstand enormous loads while maintaining their strength over decades of service. The cables are protected from corrosion by special greases and plastic sheathing that ensure long-term durability. The construction process for these pre-stressed girders follows a carefully orchestrated sequence that begins long before the actual erection takes place. The girders are manufactured at an off-site precast facility using specialized forms that ensure dimensional accuracy to within 5 millimeters over their entire 32-meter length. Once the concrete has cured sufficiently, the post-tensioning process begins. This involves threading the high-strength steel cables through the precast ducts and then applying tension using specialized hydraulic jacks. The tensioning process creates an upward camber in the girder that will be reduced to the design profile when the permanent loads are applied. The erection process uses a combination of mobile cranes and specialized lifting equipment. The girders are transported to the site on specialized trailers equipped with multi-axle dollies that distribute the load across multiple wheels. Each girder weighs approximately 85 tons, substantially lighter than conventional concrete girders of similar capacity thanks to the efficiency of pre-stressed design. The actual erection process requires millimeter precision positioning. The girders must be placed on their bearings with exact alignment to ensure proper load transfer and to maintain the bridge's geometric requirements. This is accomplished using laser-guided positioning systems and specialized bearing assemblies that allow for thermal expansion while maintaining structural integrity. After installation, the completed bridge undergoes load testing to verify its structural performance. This involves applying test loads that simulate the design traffic loads while monitoring deflections and strain levels at critical points throughout the structure. The Timf Nindia Karya Dam Bridge represents an excellent example of how pre-stressed concrete technology can provide efficient, durable, and elegant solutions for challenging infrastructure projects. The combination of advanced materials, precise construction methods, and thorough quality control results in a structure that will provide decades of reliable service while enhancing the natural beauty of its surroundings.